Hey everyone, welcome back to another episode of the QRL Show, the place where you come for the crypto and stay for the quantum. On today's episode, we have Mitchell Krawiec-Thayer and Brandon Goodell of Geometry Labs with us to discuss a macro episode on techniques for efficient post-quantum finance. And this conversation stems from a blog series that we've published over the past several months. And so any point in this conversation when we mention a blog, a part one, a part two, etc., we'll have a link to each of these that's easily accessible within the show notes for you to easily reference. And I'm really excited for you guys to be here. Also with me is Michael Strike, who is the Director of Outreach at the QRL. And Michael, I'm going to hand it off to you as we dive into this fulfilling conversation.
Yeah, thank you, Ryan. Where I want to start is if you're not familiar with our project, the Quantum Resistant Ledger is a post-quantum secure crypto blockchain project. We're purpose-built to be secure against the future progression of quantum computers. And we just had our 4-year mainnet anniversary. So we've been running for 4 years successfully, and I think that's a pretty important milestone. One of the things that we're going to cover today with Brandon and Mitchell are some of the work we've been doing from our education arm of the QRL Foundation, in which we're trying to create and propose new post-quantum cryptography schemes and solutions. So they're going to talk a little bit about that. If you're not familiar with our project, you can find us on www.qrl.org. And quite simply, that is it. And I'm going to hand this off to Mitchell and Brandon.
So just to kind of set an overview, in addition to all of these blog posts that we'll be referencing, we have open source reference implementations that are freely available on GitHub and PyPy. So if anything we're talking about sounds fun and you want to play with it, you absolutely can. So this whole kind of arc started with building out lattice-algebra, which was a math package, really, that can be used for a variety of cryptographic applications. And this automatically kind of implements best practices, constant time math, things like that. And it allows cryptography developers to really just focus on building out the crypto applications and not getting mired in like coding up polynomial representations and stuff like that. And so that library went out a couple months ago, and then we've been using that to build reference implementations for various cryptographic applications. So, Brandon, I don't know, do you want to try to talk a little bit about the digital series, digital signature series?
Yeah. So I believe that the digital signature series actually started describing the lattice algebra package. Is that correct, or am I misremembering that?
We've been calling it like 0 for lattice algebra and then 1, 2,
Gotcha.
3, 4 for the signatures. Yeah.
Gotcha. Okay. Yeah. So the lattice algebra package is a really neat way of very fluidly building the mathematics of these cryptography schemes into your computer so that most developers can just pick it up and program a crypto scheme without fear of implementation mistakes. And they can just kind of like put the algebra directly into the code. And so that was our zeroth article was describing the lattice algebra package, which I'm pretty proud of. After that, we started talking about aggregatable signatures, and I believe aggregatable one-time signatures. And one of the interesting things about aggregatable signatures is that you're able to basically, I don't want to say compress because that has this certain implication, but you're combining several signatures into only one. So in order to publish a transaction, normally you have to sign a check, right? If you're broadcasting a transaction on some sort of financial network, or you have to provide a signature. If the check is the model, like the banknote check is the model for how a cryptocurrency transaction is supposed to be, right? You have like a timestamp on it, you have an amount, you have a from and a to and a signature on it. If you could combine checks so that the signatures smush together or just add together, like literally A plus B, right? Then what you end up with is being able to throw out all of this extra data of all of the signatures that are on each check and being able to basically write only a little tiny aggregate signature to cover the whole set of transactions, which is a really, really neat way of saving space. Um, gosh. And then after that, yeah, go ahead, Mitchell.
I was just going to comment on the use cases for signature aggregation. So once we have these methods for reducing the on-chain footprint by storing one signature plus verification keys, that becomes useful in situations like multi-signature wallets, right? Where you can do the non-interactive aggregation off signature and then just put one signature on chain to unlock something. Additionally, you can imagine that this would also have use cases for on-chain governance, right? So again, you can do some of the coordination offline. You could have a M event sign off on some governance proposal. So there's a lot of applications, but we've been looking at it primarily with the motivation for proof of stake signatures. But there's a lot of potential uses beyond that.
So I'm trying to think of.
Oh, go ahead, Michael.
Oh, I'm trying to think of an analogy in which we could describe to our users, and I'm going to take for a moment. I'm going to use this is what's coming to mind: a credit union analogy. You have a check, and you deposit into your bank. There, let's say you have 5 locations. You deposit into one, and in that entry in the log or blockchain, you have your signature. You've got the date. You've got the time. You've got maybe other details, and then all of the other credit unions get consensus. They all agree that that check at some point was deposited, correct? Right, because they are the same, and it basically happens instantaneously from a consensus perspective and almost a decentralized perspective. That's an analogy for that. I guess one question that I have is, once you aggregate those signatures, blockchain has this great immutability aspect, right? But immutability just means that the data will always be there. It doesn't say what data will always be there. So when we aggregate signatures, this allows us to be able to scale the chain and the signing and keep everything with a lower data footprint. So is my understanding so far. So the question I have is, what's lost as far as being able to use the immutability and read back the entire chain and get all the data. There has to be some sort of sacrifice. I'm curious as to what that is, and if I had to think of what our users might ask, that might be a question that they would ask.
Actually, that's a really good question that I haven't thought too much about. But the first thing that jumps to mind is, since people are basically erasing their own signatures and they're combining signatures with other people's signatures, it may be hard for somebody to go back and prove that they actually, let's see here.
And my second question is going to be along the lines of anonymity. A private, it seems to me that there's some privacy based, I guess I'm going to put features in a quote there,
So actually, no, there's no privacy here. And the reason that there's no privacy here is that you're going to be able to identify each key that contributed, right? So if Alice and Bob both signed signatures and then they combine those signatures, the point of verifying those is to be able to say, Alice and Bob signed these. It's not Alice or Bob, it's Alice and Bob. So because of that, there's no real privacy thing there. On the other hand, the only real loss for aggregatable signatures is that you can't go back and find your original signature, because on the blockchain, the only thing that's written down is the aggregate signatures. But this isn't actually a problem. If the signature scheme is unforgeable, then the aggregate signature can't verify unless the original key was used. And so as a consequence, you don't need to go back and prove that you signed something. The existence of that signature is that proof. People can verify it.
The fact that consensus was already reached is that information, because
well, actually, consensus. So we're talking about a couple of different things here, right? We're talking about authentication versus what people are agreeing about what's been authenticated. Right. So for an authentication, you and I don't need to agree whether or not a signature is valid. I can put it through my own verification algorithm, and you can put it through your own verification algorithm. There's no consensus there. I mean, there's like a trivial sort of consensus there. The real thing that's going on here is that basically, sort of in the sense that, gosh, let me think of a good analogy.
I might have an analogy.
Oh, perfect.
So I thought this was a really interesting question because it's like information theoretic, right? It's like you have this many bits of signatures and then you combine them into fewer bits. So what bits went away, right? What information did we lose?
Lossy,
I think it's actually very
lossless,
interesting.
right?
I think it's lossless. The notion is, let's say I have a classroom and everyone has like a bag of marbles, and I want to know what the different colors, distribution of marbles is. The non-aggregated version is where everyone comes up, dumps the marbles out on my desk. I keep track of person A, and then we do this for each person. The aggregated version is kind of like where I just have them all dump in a bucket, and then we save the bucket. Now with the same number of marbles, but the point being, we've made it more convenient, but what we've lost is knowing which marbles belong to whom, right? And this is kind of the signatures. We smash them all together. We can still do all the numbers, make sure everything checks, everything verifies, it's lossless. And the like bits of info that went away are the like individual signatures. I could be totally wrong, Brandon. By the way, feel free to.
Okay,
which signatures belong to whom is kind of the privacy piece that I was kind of leaning in towards.
I have
a
really absurd analogy.
Go.
Really absurd.
Shoot away, Brandon.
One of my best friends once told me that I do a disservice to analogies in general. So this may be useless. Imagine you have a sock manufacturer, and everybody has their socks with their names on it. But you roll up the socks, and all of a sudden you have one pair of socks again. So you take two pairs of socks, you can roll them up together, and you just only have one pair of socks. But now instead of saying Alice and Bob on two different pairs of socks, you have one pair of socks that says Alice and Bob, and they fit both of their feet. Okay, I know that this is like a really, really silly way to look at it, but in terms of like the information loss, the verifiability is still there. You know which keys verified signatures. It's all you're doing is you're glomming these signatures together, and just you're not even gluing them together. You're just kind of like overlaying them. Some driver's licenses in some states have a little transparent window with a picture of your face on it. Have you seen these? Where like
Wisconsin has
light.
one. Yep.
Yeah, depending on the state. Yeah.
Yeah, you can kind of think of these aggregate signatures as having 128 of these faces overlaid on top of each other. And you can tell if a face is contributed to it because like if some dude has like a weird like he has bubonic plague and he has a bubo hanging off of his head like this, you can see the outline of that dude's head, right? And so you can kind of in a certain sense see which faces have contributed to it, but it's difficult to pull the specific faces out of it. And it's not necessary because you can tell that the guy with a bubo on his head is in the picture. Those are the two best analogies I have: is transparent, like laying photos on top of each other with Photoshop, and gluing socks together.
All right. So as far as SIGAG goes, I think there's 4 analogies there. I think that's sufficient, right?
I think so.
I think
I
we got
have
enough
2
there.
more, but we should probably move on.
Let's move on.
Let's lead into the next part. Yeah.
So after we were talking about aggregatable signatures, which I'm really excited about. By the way, those are all one-time signatures, which make them really hard to compare to things like crystals, dilithium, and like the NIST competitor signatures, which are many-time signatures. Mitchell and I were having this conversation earlier. But after the aggregatable signature article, we did an adapter signature article. The way adapter signatures work is that one person wants a secret, one person wants a signature. The person who wants the signature constructs a so-called pre-signature, which is sort of like a promise to a signature, and it contains the secret they want, or rather it contains the public version of the secret they want, the public key. So then they hand that over to the person who knows the secret, and they check the pre-signature, they check this promise of a signature, and if it's valid, they can adapt that. That's why they're called adapter signatures to a signature. They can adapt the pre-signature into a signature. And when they do, they can go publish it on a public bulletin board somewhere. But the minute they do, the person who gave them the pre-signature in the first place knows enough information to extract the secret out of the published signature. So verifiably encrypted signatures are sort of a way of swapping a secret for a signature, which is really, really interesting because there's a duality in cryptography between encryptions and signatures. And if you can, so like on one end of the spectrum, you have encryption where I encrypt it with my secret and then I decrypt it with my secret, and I'm the only person who knows the secret and can do the decrypting. On the other hand, for signatures, we all know what those do. We're authenticating ourselves. They're sort of dual in this respect. And as a consequence, adapter signatures sort of like straddle the fence. So one party is interested in one end of the duality and the other party is interested in the other end of the duality, and it makes for a really fun swap.
Yeah, and they got to come together in that way. Yeah.
What would be the use
Yeah,
cases,
so-
Brandon, for blockchain?
Oh, this is the coolest part about use
I
cases.
figured you got
my
a
friend.
I had a
number of
feeling
them.
you wanted that question.
Yeah, of course. So the most important use case is off-chain atomic swaps. So I can swap with a Bitcoin without any information really. Like the blockchains don't ever need to interact or talk. Computer on one network doesn't have to talk to a computer on the other, except for the two parties who are swapping. And it either goes through entirely or it fails entirely. So either nobody loses anything or everybody gets what they want, which is why it's called atomic.
So it's off. It only settles then when the base when it's needed.
Well, you set these timers into the whole transaction so that it's after a certain period of time. If it hasn't settled, the original person get their money back in the claim refund model.
Yep.
Yeah.
That's set up within the. Yep.
I'd say that.
Yeah, and it turns out that. Oh, go ahead.
No,
Michael,
please,
I'm sorry.
please. No, please.
So it turns out that claim or refund model is helpful in constructing a whole bunch of sort of smart contracty sort of blockchain applications. And I don't want to say smart contracty, I should just say flexible blockchain applications. For example, payment channels. Doing a lightning network, a multi-hop lightning network, you can do with adapter signatures. So if you were to theoretically design a post-quantum cryptography or cryptocurrency scheme using aggregatable adapter signatures, you would automatically and sort of naively be able to support off-chain atomic swaps and lightning-style payment channels without actually having to program any of that in. People could just do it on their own, which is a really, really cool feature.
What would be the secret that would get exchanged? Curious, would that be the private key that gets exchanged for a specific transaction? And
so that would
if you were
depend on who you're
interfacing with Bitcoin, okay, with Bitcoin, for example,
Bitcoin, it would be a SHA-256 pre-image, and then on the Bitcoin end of things, you'd have a pay to pre-image thing.
Okay.
So yeah, so in the end, like if I owned QRL, I could like come up with a SHA-256 pre-image and you could do like a pay to pre-image sort of thing. I'm gonna get the which party does what swapped if I talk too much, just like I did earlier. I always get Alice and Bob swapped. Yeah, so it would be something like a SHA-256 pre-image. If you're doing Monero, you would probably do something like a Kekek pre-image, or even like you might be able to do Monero keys. I remember a couple months ago, I was thinking about it, and there's a couple of ways that you can do it for in a really general sense that are extremely wasteful. So the parties who communicate might be blowing a lot of bandwidth on this, but you could get it done. So with almost any other blockchain, which is really cool.
So if I were to kind of summarize for our users, I think I agree with you. I think that you brought up cross-chain communication, atomic swaps. I think that's arguably one of the most difficult and frustrating things about blockchain right now. It'd be able to do that decentralized, without being part of a specific project like a parachain on Polkadot or an ERC20 and using Uniswap or whatever to stay decentralized. Obviously, CXs have it handled, but if I were to summarize,
do it privately over wire, right? Like if you can accomplish it privately over wire, or like Signal or some other sort of encrypted chat app, do it that way.
Right. So we're building in the functionality, but on the other end, that functionality would need to be integrated as well in order to communicate and communicate the signatures and the requested data information back and forth. So I guess the other end at the application, I don't know, I'll just call it the gRPC layer. Is that communication established well at that higher layer on the OSI, or is that just the functionality so far built in?
I believe it's the case, correct me if I'm wrong, Brandon, that to implement, say, Bitcoin QRL swaps, the work that would need to be happen is peripheral to the chains, right? It's like
Oh yeah,
infrastructure for that.
absolutely.
We don't need to modify QRL's protocol. We don't need to modify Bitcoin's protocol. Just engineer a little bit of like a P2P layer for,
Well,
yeah.
let's be careful here because QRL as it currently is not capable of doing these things.
Oh yeah. Sorry. If we were to
Right.
have
If
these
we
signature schemes
implemented this
implemented,
like
yeah,
in
yeah.
imaginary lattice-based version of future QRL, then yes, that would be like natively built in, and so anybody could come in and write an app that handled like the front end of things, and the chains wouldn't have to interact or be altered in any way. Was that what you were asking, Michael?
So still some work to do. I
Perfect.
just want to be making sure we're giving an objective perspective,
Yep.
as holistically as possible for our users. Uh,
Yep.
awesome, thank you.
And I've seen a couple dev teams work on swaps like Monero Bitcoin, and it seems like generally a good dev team can implement it in 6 to 12 months. The like surrounding infrastructure.
Yeah. Um, and that actually brings us to, I think, the most exciting, which doesn't have much to do with cryptography at all, but it has to do with coding theory, and
Is
that's
this
the
on the storage
yeah,
secure fountain architecture on that? Yeah, I wanted to go into this
yeah,
reducing storage requirements.
precisely.
Yeah.
The secure fountain architecture is so cool. So you can visualize the process as new nodes wanting to join the network. They hold out a bucket, and old nodes turn on a faucet, and they the new bucket nodes collect droplets in their bucket, and once their bucket is full, they can extract a sequence of blocks.
Yeah, and Noel, and while we're on this one, for anyone that's watching for reference, this is in part 4 of the series. So just look in the
Yes.
show notes as you're referencing this. But no, continue, Brandon.
Yeah, absolutely. So, so for the secure fountain architecture, uh, all the different nodes that want to, this is entirely optional, they can encode their blockchain into droplets, and when new nodes join the network, they can hand over their droplets. And these new nodes, these bucket nodes, can extract the blockchain from the droplets in a way that allows them to verify it as they go, so that they can discard block or data droplets from peers who are acting maliciously. And in the end, it's very, very difficult to convince a new node to decode the incorrect blockchain. So what the real value of this is that each droplet is about the size of a block. And so if you can store fewer droplets than you can blocks, then you can help new nodes bootstrap and still verify transactions after they bootstrapped without actually storing the whole blockchain locally. A lot of different blockchains attempt this striping method of pruning, and there's actually a variety of pruning methods. I shouldn't pick on striping specifically, but striping, one way that you can look at it is like, okay, you throw out one out of every, or 7 out of every 8 blocks. You pick an index from 0 to 7, and then you keep every block height that is congruent to 0 mod 8, or excuse me, that index mod 8. So you're only keeping like 1 out of every 8 blocks, but then you can't verify your transactions out of 7/8 of the blockchain, which is a lot. It's too much.
But someone else
You
could.
can only verify, someone else could. Um, However, with this droplet method, you can verify out of a significant portion of the blocks in your epic. You can still hand out droplets to new nodes. And the numbers that we're seeing right now in the original paper, the paper like provided ridiculous space savings claims, like 10,000 per, 10,000 fold. We're seeing something like 68% space savings in practice in our numbers. So we're looking at like nodes being able to throw out up to 60% of the blockchain, 68% of the blockchain, and still be able to validate transactions and still be able to help new nodes bootstrap.
And
It's super cool.
Analogy time. I have
I
one.
was just gonna say at a real quick high level, the kind of the big fundamental trade-off that's being made here is dramatically reducing storage requirements and increasing bandwidth, right? So if you have like an old iPad around the house that doesn't have a lot of storage, but you're on Wi-Fi and you have plenty of bandwidth, that'd be the kind of application. It's that trade-off. Sorry, go ahead. Analogy.
No, that was good. So for the users, I think most of our users have a hardware background of some degree. I'm picturing, as you're describing this, I'm picturing the blockchain itself, the entire ledger on a RAID 0 set, whereas where it's striped like this, not just
Mhm.
not just 3 disks, but maybe 1,000, 10,000
Sure.
disks, with the exception being that in a RAID in a RAID set that there's not any duplication of data, but in the blockchain there would be duplication of those droplets, as you say. It could be a little block. So statistically, somewhere at some point, someone is certainly to have the information that you're looking for in this distributed architecture. So not only is consensus distributed, and not only is the I don't even know how I'm going to say this. Not only is the blockchain itself distributed, but the blockchain ledger is
It's like
distributed as well. What are the words? Someone say the correct
it's
words.
like it's almost like decentralizing the dissemination process.
Exactly. It's going. Yeah.
You know what? It's not too dissimilar from BitTorrent in certain ways.
And I was going to say
Where
that one as well. Yep,
yeah.
exactly. A swarm, a BitTorrent
So
swarm of drops.
this is really cool stuff, and I actually have to thank the author of the Secure Fountain Architecture paper. I'm going to look it up really quick because I always forget it. Because first off, I've never met this person before. But sorry.
The only thing I can think of is you'd have to have a sufficiently large number of nodes, right, in order to statistically ensure that you have all pieces of the ledger, because they don't all.
So
Please.
you may need to contact a larger or like a decent number of nodes. But the numbers that we're looking at, we're designing it so that if you can contact 4 honest nodes, then you can reconstruct the blockchain
Is that statistically or guaranteed?
in expectation. So it's just statistical. Okay, so but real quick, I want to thank the authors of the Secure Fountain Architecture. I'm going to butcher their names, Kade, Chung, and Ramachandran, who basically employed the Luby transform code, the LT code, by bootstrapping the hash chain, right? So the reason that this works is that you can throw out droplets from malicious nodes, and the reason that you can do that is because you maintain the hash chain. So once you've decoded a block, you have that block's payload. You can compute the Merkle root. You can compare it to the hash header that you're expecting, and you can see if all the hashes are working out. And if that didn't work, then you can throw that droplet out. And this is like a really, really brilliant observation. And it was actually introduced to me by a mathematician named Felice Manganiello at Clemson University when I was at a Bitcoin conference in Toronto at the Fields Institute a couple of years ago. And I've literally been trying to like figure out exactly how efficient this paper could get for a while. And then QRL was finally like, okay, how about you tell us how efficient this can be? So I finally had a reason to like look into it. So yeah, anyway, I'll stop rambling now.
And Michael, back to your question about how to couch this in terms of like centralization and decentralization. I think the like thought experiment that comes to mind for me is if you imagine something with a 5 terabyte blockchain, that's going to have a massively centralizing force in if you don't have secure fountain architecture, and every full node has to have 5 terabytes. At the time of recording, that's a lot of disk space for like a regular commercial laptop or resident, whereas if you switch to the secure fountain architecture and you've tuned it for like high space savings, high bandwidth usage, now you can actually run all these full nodes on much lighter devices, your laptop, and it's just on the fly getting and discarding data that it needs. And so that's where
Well,
I
let's
would
say
say
nearly full nodes. Nearly full
yeah,
nodes. Yeah.
nearly full nodes. And so that's then where the kind of decentralizing comes into play. Is you've dramatically lowered the space requirements and made it more accessible.
More scale.
And also, one interesting observation I made just the other day is that the bandwidth cost of this method actually goes away if there are still full nodes around just serving up droplets. So people can, or excuse me, just serving up blocks, because people can just download the blocks instead of the droplets. So the overhead actually vanishes.
So as we're talking about,
which,
sorry,
68% storage savings with no overhead. Like,
so as we're talking about bandwidth, saving bandwidth, we're talking about
Mhm.
reducing the payloads and possibly reducing the size of the packets. With that being said, bandwidth isn't really, it's not really a big problem today as it is, right? But we are making
increasing bandwidth. with this method we increase bandwidth. We're trading storage space for bandwidth, so we're increasing bandwidth
Correct.
in
Yeah.
exchange for
Right.
storage
Right.
space.
Right. Of course.
Now, this is actually arguably sort of a useless method if we cite the incorrect Moore's law, right? Storage is getting cheaper and cheaper and cheaper, so there really isn't a good reason to offload storage onto bandwidth, because in the end, bandwidth is going to be what's expensive, which is what I think you were getting at, Michael. Is that 25 years from now, I'll be able to have 5 terabyte hard drives like just on little SD cards all over the place, but the price of the internet is going to be the real
But
cost there.
there's also Nielsen's law, which is that high-end user connection speed grows about 50% year over year.
Okay, well,
And there's
so
also
okay,
So
Nevin's
we have
Nevin's
both
law.
laws. There's both laws.
And there's Nevin's
okay, so
law,
two
which is why we're
incorrect
all
laws.
here.
Yeah. And then there's Jevons Paradox, which I love. Are you guys familiar? This actually bothers the crap out of me.
I might when you reference, but it's not jog my memory.
I believe that a lot of viewers may know this because this is sort of a famous economic issue or economic paradox that cryptocurrency people like. Jevons Paradox basically says that if you increase the efficiency of a system, the usage of the system will increase until the efficiency is maxed out.
Like hard
Okay,
drives.
So
now
it's the reason that
Yep.
adding more highway lanes just leads to more traffic. And so actually every time that we do one of these efficiency improvements, Jevons Paradox is sitting in the back of my mind, and I'm like, oh, this just means people are going to be using the space a lot more, which is a good thing, right? But
And that's true. I mean, if we all had 1 terabyte drives, Chia probably wouldn't have taken off as it did, right? We use what we're given. We'll always find ways to use resources.
That's very wise, Michael. We live in the worlds that we build for ourselves. We use what we get.
Where I'd kind of like to wrap up and close things now that we touched on the storage requirements part and part 4 there is before we close out this episode, we're going to be doing an upcoming episode, which is going to be an AMA episode on the entire series. But wrapping up this episode, I'd like to give either any key takeaways for those who are watching to kind of walk away with, either as like a reminder of a few things to keep in mind, or maybe just some lanes to potentially go down. I know that there's a lot of complexity as people go into each part, but really where's maybe a couple key takeaways or parts where they can maybe at least build their own rabbit hole, so to speak. Brandon or Mitchell?
I'll let Mitchell start.
And just as an added part, Mitchell, I know we talked on, this is kind of, there's parts of part, 0 through 4, but also, it's a continuation. So I kind of want to keep people's, intrigue going as far as, this is a continued thing. We don't just stop here. This is, an evolution to it. So wherever you want to, lead viewers.
I would say if I had to give a 1 to 2 sentence comment on the various portions, I would say, like, to me, one of the exciting takeaways over the kind of signature portion of the series is that these new lattice algebra techniques based on quantum hard assumptions are really cool, not just in that they are quantum secure, but also hopefully scalable. Also, you can bring in all this extra functionality. It's just a really cool, really active field of research. A lot of this, there's all these now, zero knowledge arguments being built on top of that, all of that. So if there's like crypto nerds out there, this is, I think, a really cool thing to kind of drill into and just start learning about. And then in terms of the secure founder architecture, I would say, I think the big exciting takeaway here is that this is just kind of a general tool that could be applied to any blockchain, can be tuned for whether you want to like really drive down to space storage or not collect any peers. Uh, and I really think that this could become like a pretty standard second layer. And so stay tuned for that. I think we'll have a lot of cool developments there. And who knows what articles we'll have coming out after this.
No, I
Yeah, I
appreciate
think
appreciate that. Yeah.
I think that for people interested in signatures and cryptography, they can keep an eye on the latest NIST competitors and the competition winners that just came out. I believe Falcon, Sphinx, and crystals were the signature schemes that came out of that. As far as I know, none of those are aggregatable right now. So keeping an eye on aggregatable versions of those guys would be an interesting thing. Falcon has a ring signature version of itself that somebody used a couple of years ago to design a post-quantum version of Monero, which was kind of an interesting thing. Let's see here. As far as adapter signatures go, that honestly has so many different names in the literature and stuff that, like, literally we've consulted with cryptographers to like look through articles, and they're like, I've never heard of adapter signatures. What are these? I'm like, well, what about verifiably encrypted signatures from this paper? And they're like, ooh, it's real inside baseball. As far as secure fountain architecture stuff goes, coding theory is an area of mathematics that deals with basically compression and decompression. I don't want to like oversimplify things, but you can think of what we're doing here as compressing the blockchain into a couple of droplets, right? Coding theory is a field of mathematics that doesn't deal with trying to keep information secret, but there's things like error correcting codes, so that if I'm transmitting information over a noisy channel, you can make sure that you get the whole thing, which is one of the ways that these video calls work. Otherwise, like a noisy channel will corrupt the video. There's a variety of interesting coding theory questions. For example, it's not even really well known how the best, or what the best method is to encode. Let's say you have a bit string of 256 bits, and you know 60 of them are 1 and the rest are 0. How do you optimally encode that bit string? Like, that's an open question. And it's related to crystals dilithium, the signature scheme, because that describes how their signature challenges are computed. And yeah, I mean, honestly, the best rabbit holes come from just going from Wikipedia article to Wikipedia article until you don't find the articles anymore on Wikipedia, and you have to go to the references, and then you follow the references through those, and you just merrily go down your rabbit hole.
Yeah, no, I appreciate it. And I think also, as well, as anyone that's viewing this video, we have in the show notes, we have references and links to all of the parts within the series. So even if you start at the first one, kind of go through that and then take Brandon's recommendation of going across referencing it with Wikipedia and just, building your own rabbit hole for that. That's probably the best way to go about it, depending on where you are in your journey of how much you want to know about it, and how in depth you want to get. Michael, is there anything else on your side before we wrap up this episode? I've appreciated Mitchell and Brandon the conversation.
No, thank you guys so much. I'm going to take everything that we said and summarize it into a few basic thoughts, or at least attempt to. Essentially, if in blockchain, in programming, let's make this real simple. In programming, if you want to encrypt something or decrypt something or perform some sort of cryptographic function, you're not writing this code today. You're not writing up and redesigning ECDSA and all stuff. You're going to use what's the best analogy? I'm just going to call it a DLL. You're just going to use a library, right? So you don't have to be an expert at understanding, and that's how it's done today. What we're doing is just doing the same thing so that other projects can use the libraries, except that they're post-quantum computer secure. So I'm making things real simple, but I'm sacrificing here a little bit, but in real simple, essentially we're building off these libraries that can be used in other projects and be post-quantum secure so that they don't have to become experts on post-quantum technology. Feel free to close and add in anything else.
Well, it's not so much that, I mean, expertise is avoiding expertise. So there's a famous saying in the crypto world, which is don't roll your own crypto. And in a sense, the lattice algebra library that we came out with is designed so that people can roll their own crypto in a way that is safe. And I don't want to say safe, right? But it removes a lot of the dangerous aspects of rolling your own crypto, especially in lattice computations, things like non-constant time arithmetic. I'm not sure if you guys heard about the recent 0-day exploit Hertzbleed.
I think I crossed it.
Have you heard of that?
It's only been 0 days.
Well, yeah, actually, I'm not sure if it was a 0-day, but a recent critical vulnerability came out called Hertz bleed, and what it does is it looks at how long your or how your CPU is being throttled up and down, and then it uses that to determine what you're computing on. So, like, I mean, a couple of years ago, some guys put a microphone in a room with a computer while it was encrypting and decrypting with RSA, and it was able to like crack 4,096 bit keys. We're talking about like supposed to be 4,096 bits of security, and they cracked it just by listening to the machine. So, anytime that you have something throttling up and down, it's dangerous. So like you want your arithmetic to be happening in constant time so that every operation takes the same amount of time. Every single time you do the thing, it takes the same amount of time. Your CPU won't throttle itself. And that's what our library is intended to do, is to try to remove all those scary things that you don't necessarily think about unless you have been studying crypto for a long
And
time.
I just
So
have
yeah, I apologize, Michael. I went down
nope. That's
I think
okay.
we like
rabbit hole
remove
there.
the mistake surface. Instead, you could like make mistakes doing the
Yeah.
math or make mistakes doing the crypto. People can still make mistakes doing the crypto, but we've now like kind of shrunk that oopsie surface.
Yep. The oopsie surface. Love it.
That's a technical term.
Yeah. Yeah, we'll take that to another episode outside of the ELI 5. But no, guys, we really appreciate that conversation. As mentioned a minute or two ago, we're going to be having an upcoming AMA on the whole series that we've gone over. So if you have any good questions, big or small, that you want to ask for that, the link for the AMA will be in the show notes as well. Post in the comments or ask within any of our social communities, Discord, etc. And Brandon and Mitchell, yeah.
For the record, for that AMA, if anybody wants to ask me calculus or differential equations questions because they're taking a summer class, I will answer.
Even better. There's no question off the limits as long as it's helpful for everyone. We already got a couple dozen questions for that, so ask away any questions. And Brandon and Mitchell, from myself and Michael, we appreciate the conversation, and we will see you in our upcoming AMA. Appreciate it. Thanks.